Okay, so on to exam 3 study guide. So these are going to be the free answer part of the of exam 3. Right? There's going to be, I think, 4 or 5 multiple choice questions, stuff like that. But these are going to be the free answer part, stuff like that. So first up will be the degree of unsaturation. So I will give you that equation. I'm not going to give you the key, but I'm going to give you that equation. You're just going to need to know how to use it. Right? So I'm going to give you some a formula like this, and you've got to be able to calculate that degree of unsaturation. So C6H H10Br2. Okay, so put that. So DOU. Right, so it's 2 times the number of carbons, right, plus 2. Mm-hmm. We don't have any nitrogens in there, right? So don't worry about that. We do have two halides, right? So like that. So it doesn't matter if they're, if you had a bromine and a fluorine, or a chlorine and a bromine, or something like that. It's still, you just have 2. The total number of halogens is 2. Okay, so it's minus 2 minus the number of hydrogens, 10. Okay, so divided by 2, right? So 12, 14, right? Minus 12, right? So divided by 2. 2 divided by 2, 1. So you have 1 degree of unsaturation in that, right? So for C5, H8 into O2, right? So DOU, right? So just use that equation, right? So 2 times 5, right? So 2 times the number of carbons, right? Plus 2. Plus the number of nitrogens, right? So we have 2 nitrogens. Minus the number of halides, right? We don't have any halides in there. Minus the number of hydrogens, 8, all divided by 2. Right? So 10, 12, 14. Right? Minus 8 divided by 2, right? So that's 6 divided by 2. So that's 3. Okay, notice that oxygen does not come into play like that. So don't add that to your equation, right? So like that. So don't add it. It doesn't come into play in this calculation. So you can ignore that. Right? So that's just carbons, nitrogens, halides, hydrogens. So like that. So there we go. Right. Okay. Next up, naming of alkenes and alkynes. So like that. So for alkenes, you're going to need to put the cis and trans in there. So like that. So alkynes you don't need to, right? Because there's only one thing sticking off on either side, right? So that carbon already has 3 bonds to it, so it can only have one other thing hanging off of it. So like that. So you don't need to worry about cis and trans there. But for alkenes, because you can have 2 things hanging off of each carbon, right? Besides the double bond, you need to know where they are in space. Okay, so here we go. Okay, so fill in the, you can put in the dots where the carbons are, right? If it helps, right? So here we go. So remember the longest chain has to go through that double bond, right? So first step's always finding that longest chain, right? So it has to go through here. So you might as well start there. So 1, 2, 3, 4, 5, 6, right? Don't forget to go through the side chains. 1, 2, 3, 4, 5, 6, right? So it's actually not going to matter which side you go on, but just out of habit, we'll do the horizontal chain. Okay, so like that. So it's 1, 2, 3, 4, 5, 6, right? So it's C6, which the base name is just hexane, right? But we have to indicate that we have a double bond in there, so it becomes hexine. Right? So double bond. Okay, so we're going to need to know where that. So right, so we have this as a side chain. Okay, now we're going to include the alkene, right? Because we need to say where that starts, right? And then we also have this 2 carbon piece, right? 2 carbon piece that makes it an ethyl. Okay, so we need numbering, right? So we start on the side. We don't have to do both sides, right? We just need to know the start of carbon 1 on the side that ends up closest to that double bond. So it's only going to need to be this one here. So 1, 2, 3, 4, 5, 6, right? So with that, so the alkene starts at carbon 2, right? And then the ethyl group is at 4, right? So first off, right? So this alkene, right? So that we need to say where this ene is. We don't have to put alkene in there, but that's what the ene is for. We need to say where it starts. Okay, so it becomes 4 ethyl, right? 2 hexene, right? But we need to know which configuration, right? Is it cis or trans, right? So if you can, I always look at where the hydrogens are pointing, right? So there's hydrogen there and there, right? Because there's, right, 3 bonds shown, so there's a hydrogen that's not written, right? Same here, right? So the hydrogens are on the same side, right? So they're, you can sort of say this side's the upside, this side's the downside, right? They're both pointing down, so it becomes cis. So here's the name, right? So we have a 6-carbon chain, right? Right, with a double bond in it. Where's that double bond start? Well, it starts at carbon 2. Okay. And that double bond is in the cis configuration, right? So that hydrogens are on the same side. Oh, hey, we also have an ethyl group, right? Where is that hanging off of the main chain? Carbon 4. So, okay. Next up, we got this guy here. Right. So put in the dots for your carbons. Okay. So again, our main chain has to go through the triple bond, right? So here you go. So 1, 2, 3, 4, 5, 6, 7, 8, right? 1, 2, 3, 4, 5, right? Don't forget to go down in side chains, right? 1, 2, 3, 4, 5, 6, 7. Well, looks like it's going to be the 8. So here it is. All right. So C8. So normally that'd be octane, right? But since we have a triple bond, right, it's octyne. So that's going to be our main chain. Okay, so we're going to have, right, so our alkyne, say where that starts, right? But then we also have that methyl group, and then this propyl group, okay? Because it's, right, it's 3 long, 1, 2, 3, right? But since it's connected to the main chain through the carbon 2, right, we call it a 2-propyl group, okay? You could also call it an isopropyl group. I like 2-propyl because it's a little more descriptive. But anyways, so right, so we need to get the numbering on the main chain, right? So we need to start on the side that has the triple bond, right? So with that, so this side is closest to the triple bond, obviously, because carbon 1's attached. Starts at carbon 1, right? So 1, 2, 3, 4, 5, 6, 7, 8, right? So the alkyne starts at carbon 1, right? The methyl group is hanging off of carbon 4. Right, and the 2-propyl group is connected to the main chain through carbon 5. Okay, so the right, so put the name on here, right? So you just compare methyl and propyl. Now, it would not matter if you wrote isopropyl; it's still the propyl. It's methyl propyl. Just like we don't consider di and tri and that kind of stuff, we also don't consider iso. Right, so it'd be methyl versus propyl. So the methyl wins, right? So it's 4 methyl. Okay. 5, and I'm going to put the parentheses in here just so you know that we sort of bolt the 2-propyl in just like right there. Okay, 2-propyl, just like we bolt the methyl group in there. Put the 2-propyl. Okay, 1 octyne. Okay, so what do we have, right? So we have a main chain that's 8 long, right? And we also have a triple bond in there, right? Where does it start? It starts at carbon 1. Oh, hey, we have a 2-propyl group in there. Where is it connected to the main chain? It's connected at carbon 5. We also have a methyl group, right? Where is it connected? It's connected to carbon 4. So there we go. Okay, so E and Z. Okay, so this one here, we're going to need to use similar rules as the R and the S for priorities. Okay, so with that, so what we do is we cover up one side, right, and we say, okay, here we go. So we have chlorine versus nitrogen, right? So with that, so which is going to be the higher priority? Chlorine is heavier, has a higher molecular mass, right? So this gets the high, and this gets the low. Okay. Now in this, and then you say, okay, I'm going to cover up this side, right? And then you do the same priority rules, right? So CH2s. Here's this CH2, CH2, CH3, right? CH2, CH3. Okay, so this guy here, right? So this guy, right? So it's a tie, right? Carbon versus carbon, right? So this one has two carbon-carbon bonds and two carbon hydrogens, right? Same goes with this one, right? Two carbon-carbon, two carbon hydrogen, right? So it's still a tie, right? So when we get a tie, we go out one further out, right? So like that. So we compare this one with this one, right? So like that. So now for this one, right? This one has two carbon-carbon and two carbon hydrogens, right? This one here, right, only has one carbon-carbon, three carbon hydrogen. Okay. So with that, so this one actually, so you compare, right, the heaviest thing hanging off, right? So this is 2 versus 1, so this becomes the high, and this becomes the low. Okay, so with that, so the highs are on the same side, right? So, right, so if it's Z, right, so it's on the same side, right? So you can do your best bad German accent. It's saying like it's on Z's same side, right? So right, that's it, and then E is opposite. It's a quirk of the, right, so you would think the Z, right, you know, these things are pointed, you know, the top and the bottom of the letters are pointing opposite. Well, and then, so it would be, you know, these would be opposite, and the lines are top and bottom of the letters are pointing the same way, so the opposite, but it turns out that it's a quirk of the German language, that this means the same, and this means opposite. This means together, I believe, and this means apart, stuff like that. But here we go, so right, so the high and the high are both up, right? So if you think this is up and this is down, right? This is up, this is down, right? So they're both up, right? So this becomes, they're on Z same side, so it becomes Z. Okay, so for this one, right? So like that. So okay, so we right. So we're going to compare that, right? So that's CH2, CH3, right? Right. So hydrogen versus carbon, right? So this is the low and this is the high, right? Because carbon's heavier, right? So on this side here, right, we have CH3, CH2, CH2, and then the chlorine, right? So here we go, right? So we have carbon versus carbon, right? So it's a tie, right? So this is two carbon-carbon, right? Two carbon hydrogen, right? So this one here, right? It's one carbon-carbon, right? Three carbon hydrogens, right? So compare that to this, right? So with that, so it's so this gets the high, and this gets the low, right? So you compare the high. This is up, this is down, right? This is up, this is down, right? So the high is up versus down, so it's opposite each other, right? So this is the E. Okay, you have to be, just like with the R and S, you have to be very disciplined to go here, and then here, and then here, and then as soon as you find a difference, you stop. It doesn't matter if there's, you know, if this thing had, you know, if you go out here and this, you know, this is really short, but it had a chlorine here, and this was really long. As soon as you find a difference, you stop. You have to be very disciplined, just like the R and the S work. So please be careful. Okay, so potential mechanisms, right? So here are the three potential mechanisms, right? So with that, so you are going to, I'm going to pick on your exam. You're going to have one of these to deal with. Okay, so with that, so it's just you don't know which one, right? So you need to know the three. Okay, so with that, so we'll actually talk about the next slide is this one here. But we'll go through this mechanism there. That middle one, just to show you what I want to see, right? So I'm going to draw it out, right? So let's say it's this plus, you know, it'll probably be written like this: Br2, H2O. Okay, so the Br2 is actually, you can sort of think of that as that, right? Okay, so okay, so. Right, this has negative character, right? So this spontaneously, this part's going to have plus and minus character, right? You don't have to put the partial charges. Now, if you have an actual formal charge, you're going to have to write that. And if you have a resonance structure, you're going to have to write that. But partial charges aren't that big. That's not, that you don't have to write. But this one here, right, that's going to attack that. Bromine, right, so it already has it's 8, so it's need to get rid of 2. So what it does, it takes these, pushes those electrons onto there, right? This is the same mechanism we dealt with the last exam, right? So, okay, so, oh, and I would actually show you what the product is, right? So for these curved arrow mechanisms, I'm going to give you what the product is. So this is actually what the product would look like, although you could predict it if you wanted to, like that. So, okay, so the bromine, right? So 2 reasons why it's going to want to come over here, right? For starters, right? So if bromine goes here, right, that means that the positive charge is on the more substituted, right? So this is secondary, right? Because this carbon here is attached to 2 carbons, has 2 carbons attached to it. Well, this one here has only one carbon attached to it, right? So this carbocation is going to be more stable. The other reason why you know it goes there is because it's written that it goes there on the product. Okay, so like that. So the nice thing is, right? So here we go for the resonance structure. Okay, so right, so you have a positive charge here. Okay, and so these electrons there, they are going to be attracted to that carbocation there. Okay, so you're actually going to get a nice resonance structure to help stabilize this. Oop. Oop. So the positive charge is up here, right? So that those electrons there become this new bond here. Okay. So like that. So this is a resonance structure, okay? And so we also made, obviously, Br minus, okay? But what can happen is, right, so this is what stabilizes it before something comes and attacks. Well, this water is going to come in and attack, right? Before this bromine, because this is a really terrible nucleophile, before this thing comes back and attacks, you're going to have this guy come in, and attack there, right, to make this. Right, so the water is going to come in for the backside, right, and then the bromine can come in and grab one of these hydrogens, okay, like that, plus HBr, okay, or another water can come in and attack whatever. So like that. What I want to see, right? So I want to see these formal charges here and here. I need to see where the electrons go. I need to see the resonance structure here, like that. So and where things fall into place. Right? So that would be what I would need. Okay. Another one would be like this, right? So it's very similar to it. Okay. So again, you can predict it on a curved arrow mechanism. I'll show you what the product is, right? But we have a bromine, we have a double bond, so it's going to end up looking like this, right? So if you wanted to predict it, you could, but on a curved arrow mechanism on an exam, I'll give you what the product is, right? Because I could test you this later in the exam. Okay, so again, it's very similar to what we were doing before, right? So, right, bromine. Right, so you're going to have the double bond attack, right? Push these electrons over to make this intermediate. Right, this is going to be the more stable carbocation, right? But you are going to get these 2 electrons, right, going to be attracted to that positive charge to make this resonance structure. Okay. Yeah, you also made, and don't forget, you also made the plus the Br minus. Right, but now we don't have water coming in here. Right, so now it's got to wait for the bromine to do its thing, right? Right, so now that comes in and attacks, and there you go. So, right, so this set of electrons was to make that resonance structure, but the resonance structure is there to just stabilize the molecule until the bromine gets enough motivation to come in and attack that carbocation there. when it sees, right, so this one's going to be attracted to there, right, so eventually this thing will come in and attack this structure here and go there. So. Okay, hydride and alkyl shifts. Okay, so I'm not going to make you predict it, right? So what's going to happen is you're going to have a structure, and it's going to say draw a curved error mechanism to explain what the heck happened, right? So you have HBr, right? So okay, and how are you going to know that it's a hydride shift, right? It's because the HBr does not add directly onto this double bond. Okay, it's adding here, right? Right, so like that. So, okay. So usually the best thing to do with this is to just go ahead and draw out all the hydrogens. Okay. Sometimes easier to see what's going on. Okay. Okay, and so what's happened is, right, so there's a hydrogen missing, right? So on this carbon here, right, you have a methyl and a bromine. Right here, you've got a methyl and a hydrogen. This hydrogen has gone somewhere, right? Something like that. So we're going to have a hydrogen shift actually over to here. Okay, and so how does this mechanism go? And so again, right, there's going to be a partial positive there, partial negative there, right? So this has a partial negative character, right? So that goes there. There. Right, like that. So why did I put the carbocation there? Well, because eventually the bromine, right? So this is bromine, right? You also make bromine. The bromide's eventually going to have to tack there, okay, because that's where the positive charge is going to end up having to go. Okay, we can't go across. We can't go two away. Right, so like that. So but we can get we can go one carbon away, right? So like that. So what happens is this hydrogen here shifts there, right? So like that. So when that happens, we get this. Okay, and so that hydrogen there ends up becoming that hydrogen there. Why does it go there? Right, so this carbon here, right, it has one carbon attached to it, right, so it's secondary. Now this carbon here has 1, 2, 3 carbons attached to its tertiary. So a tertiary carbocation is going to be much, much more stable than a secondary. Okay, and that's when this guy can come in and attack there to make that. So the justification for this is the hydride shift. Okay, so there we go. Okay, so this is the reaction summary. Okay, so these are the different types of reactions, right? For the alkene, right? So the X is just going to be a halide. So in theory, it'd be fluorine, but fluorine doesn't work. But it's usually going to be iodine, bromine, chlorine, things like that. So those all do those same things. Okay, so you're just going to need to know these the alkenes and their corresponding alkyne, sort of with the alkynes as well. So, okay, multi-step synthesis. Okay, so this is probably going to be the quirkier part of what you're needing to know, right? So this is some of the students have a hard time. So if you're struggling with this, don't be too worried about that everybody else is getting it and you're not. That's not what's going to happen, right? So everybody struggles with this in the beginning. The biggest part, right? So usually the way these work is that you're probably going to be putting in some sort of functional group. And usually what you're going to want to do is you're going to say, how do we put in that functional group? The second half of the synthesis is going to be putting in that functional group. Okay, the first half of the synthesis is probably going to be building up the carbon chain to get to that point. Now, it's not 100%. It's a rule of thumb, which means sometimes your thumb gets smashed, right, and it doesn't work that way. But probably 9 times out of 10, that's what the synthesis is going to be about: getting the carbon chain to where you need it to go, and then that last part is figuring out where this is. Okay, so like that. So how do we make ketones? Okay, so with that. So the way that we know that, so probably the easiest way to know that is to take a triple bond. Oops. Okay, and then either do right. So it's not a methyl. It's in the inside, right? So it's not a methyl ketone. It's not an aldehyde. Okay, and so it really doesn't matter if we do the mercury version, right? So like that, or the BH3 H2O2. Okay, so this one, says goes right. So we put on the OH here, right? So like that, and then to make the double bond, but that tautomerizes to this, right, to the ketone. But then that also what happens with the BH3, right? So like that, this goes on the more substituted, this goes on the same on the less substituted. But in this case, right, if they're both the same, it'll do both ways. Okay, and so what we can do is if the molecule is symmetrical, which it sort of is, which I'll show you in a minute how that would work. Right, it actually doesn't matter which one, right? So really, what we need to do is we need to get to just a triple bond that's symmetrical on either side. Okay, and so what you do is you take here's your sort of carbon store that you can use, and then you can use whatever reaction you want. Okay, and so here's a triple bond, right? So which we're going to need for that last step. And so what we really want to do is we really want to look at it something like this, right? So being a Purdue guy, I like hydroboration. So right, so what the molecule is going to want to look like is this. Okay, and you can say, well, there's no difference between the, well, what if it needs to go here? If you were to go here, right, it's actually the same molecule, just flipped, right? So put the OH here, right, which is the same, because since the molecule is going to be symmetrical, it just flipped. So it really doesn't matter. Okay, so it's really this what we're looking for, right? So that's going to be the last transformation. Okay, so we really need to build up the molecule to get to that step. Okay, and so here is acetylene, right? So there's that acetylene, and so really all we need to do is we need to add an ethyl group on either side. Okay, so like that. So what we really need to do is we need to start with something like, I'm going to start down here. Start with acetylene. Okay, and add sodium amide. Okay, all right, to make the HC, to make the carbanion, right? And then you add, right, the 2 carbon piece, like that, and then you go through this process again, where you add sodium amide, and now you take off the other one, right? And then you add another equivalent of the ethyl bromide, and then you get to that. Okay, and so this first part, right, is to build your carbon skeleton. Right? And then the second part here is to put on functional group. I should say install functional group. Right? We're not going to put a 20-step synthesis in an exam, right? You only have an hour to do it, right? So you need to know what this last step is going to be, and then you know what your target for your carbon chain is going to be, right? So here is the CH3, right? The acetylene. I'm sorry. This is the acetylene here, and then you just add the 2 parts onto it, right? So it's really sort of starting here, right? And you knew you needed this, right, from the chemistry. How do we put in a ketone, right? And then you needed to know what was on either side. Okay, so this is the route. going to it. Okay, the first half is going to be build your skeleton. The second half is install the functional group. It's not 100% of the time, but it's 90% of the time. Stuff like that. So there we go. Okay, so again, how are we going to do that? Okay, so here we go. So we're going to go to our carbon store, right? So how do we make us, right? So, right, don't forget there's hydrogens here, right? So how do we make a cis double bond, right? Well, we start from a triple bond, right, and do a H2 with Lindlar. Right, so that's going to be right, so there we go. Okay, so you can start with acetylene and then just put methyl groups on either side. You could do that. There's more than one way to deal with these things. The other way to do is just start with this one. Okay, and so I'm sorry, I got ahead of myself. Right, so the last step, okay, that put in the functional group, right? In this case, it's that cis double bond, right? So we're going to need our molecule to look like this, right? H2 Lindlar. Okay, so it's really we need to build that up. Okay, so again, this is the install the functional group, and now we need to build up that carbon chain. Okay, and so what we can do is we could start with just that acetylene group and then add methyl groups on here. But I did give you the option of doing that, right? So we can just start. We can add that. We can start with that group, right, and just add the methyl, right? So here we go. So we can start with this, right? NH and H2, right? So CH3, and then you just add the CH3 Br, right? But again, this is install functional group, and this is build, right? Build carbon chain. Okay, stuff like that. So there we go. And so here's another. Oh, I see what happened. So this is the problem with this one, right? So I combined two. I didn't look at this more closely, right? So here you actually just start from there. If I were to start from the double bond, right, so like that. So this is what happened originally. So I used to not give the carbon store, right? So I would give you what you need to start with, and I originally had you just start with that right there, the acrolein. So like that, and so to make a double bond, you still need to do this process, right? But you had to, right? So you had to make the triple bond first. And so how do you do that? You take the double bond down to a single bond by adding bromines across to add excess KOH to make that, like that. So sorry for the confusion, right? So I changed it here to make it look more like what the exam was going to be, but I forgot to change the sign. So sorry about that. So here we're just starting from that point there. So sorry about that. Sorry for the confusion. Okay, so now here's another one. So for here, if I don't give you the carbon store, that means I've given you all the carbons you need, right? So like that. So for here, right? So like that. So you don't have to install any. You just need to know the functional groups, right? So here we go. Okay, so how do we, right? So how do we install a methyl ketone, right? Well, right. So we can't start here, right, and do like an oxymercuration, right? Because we can't put like a triple bond there, right? Because it's gonna be right, half it's gonna go there, half it's gonna go there. Which, I mean, I guess you could say you could separate them, but I'd really rather have you just build the one compound. The other way that you could do this to put a methyl ketone is to start with a terminal alkyne, and since the double bond is there, that's probably what I'm looking for. Okay, and so what you can do is then you do the oxymercuration, right? So which installs that, right? Which tautomerizes to, right? So it's to CH3. I'm sorry. That. Okay, so we're going to need to get to that. Okay, so that last step, right, is going to be this with this mercury compound, right? So with the oxymercuration one. Okay, so how do we make a right? 2, 4, 6. Oops. Sorry, forgot to put an extra carbon there. 2, 4, 6. Okay, so how do we get there? So how do we transform a double bond into a triple bond? We saw that previous to that, right? So you have to, right? So you have to add bromines across it, right? Right, and then add KOH, right? So excess KOH. Okay, and so here you don't have to add the carbon, right? So it's just basically how do you build the functional group in, okay? Stuff like that. So here, if I don't give you that carbon store, that means you have all the carbons you need. So for here, you can come in like that. You have to install the triple bond and then do that. Stuff like that. So in order to put in that triple bond, you have to do a two-step process. Add the bromine, and then add KOH to it. Okay, there you go. Okay, the other last thing I'm going to do, okay, is a set of reactions, right? So you're either going to be, it's either going to be predict the product, or you have to tell me what the chemicals you have to put in to do the transformation. Okay, and so for the first one, right? So wherever that question, right? There's three things, right? So there's products, chemicals, products, chemicals, reactants, right? So I'm going to give you only two of them. You got to tell me what it is, right? So if you have this, right? You have ozone, presence of zinc, right? So in order to do that, right? You slice it in half, right? So remember, there's a hydrogen here. Okay, you slice it in half. You put O's where that double bond is. Okay, and so over here, right? There you go. If you want to redraw it, right? So it's 1, 2, 3, 4, right? So it's 4 carbons and an aldehyde at either end. But I would accept this, right? You're less likely to add or subtract carbons, right? If you just draw like that. Okay, so there we go. Okay, so for this one here, right? Right. So what does it take? Right, so we're turning a double bond into an alcohol, right, on the less substituted side, right? So this is, right, so that's a secondary carbon, right, because it has 2 carbons attached, right? This one is the primary carbon, right? So we're putting an OH on the more substituted side. So we do that with the mercury acetate. Okay, H plus and water. Okay, this one here, what happens when we HBr, right? So we're adding, right? So it's just like a, so doing it with the triple bond is just like adding it with the double bond, just doing it twice, right? But remember, right, the first thing that gets added, right? So you add there, so you're going to add the H here, and you're going to put the carbocation there, right? Because it's the more stable carbocation, right? So when that happens the second time, again, this is going to be the more stable carbocation, right? So when this reaction happens, both the bromines are going to come here. Okay, they go to the same side. Okay, so for here, so how do you turn a double bond into an epoxide? Right, that's MCP. Metachloroperoxybenzoic acid. Okay, so what happens if you have osmium, NMO, right? So if you're on a ring, right, not only do you get osmium puts OHs on either side, but they're on the same side. Okay. Remember, it's cis addition of the osmium. Normally, if it's just a regular straight chain, it doesn't matter, right? Because you get free rotation. But here they're stuck, and so here you indicate that they're going onto the same side. Okay. And lastly, right, so about that. So what adds a chlorine on, right? So yeah, let me draw this a little bit better so it's a little bit easier to see. Okay. Right, so normally when we add a chlorine across a double bond, right, you put a chlorine here, but we've added the OH, so we've added the chlorohydrin, right? So how do you do that? So the chlorine comes from, the chloride comes from the chlorine, right? And the fact that we've had you do it in water, which is where you get the OH from. Okay, so there's going to be a series of reactions like this where there's going to be a question mark, and you got to figure out, you got to let me know what's going on. Okay, and so that is the free answer portion of the exam. So the multiple choice question is going to be some trends. A couple of them are going to be some that you should know pretty easily. But again, just look at trends and some sort of general knowledge stuff. So good luck.